In this video, we're going to talk about taking derivatives of trig functions. So you need to know how to take the derivative of basic trig functions. The derivative of sine of u with respect to x. That is, u is in terms of x. It's probably more complicated than u just being x. So you're taking the sine of something complicated in terms of x, and you're getting back the cosine of that same function. But then you have to take the derivative of that angle. The derivative of cosine of u is negative the sine of u. But instead of x, we have u. So we need to take the derivative of u. Whenever you replace something that you know the derivative for when it's just x, you can plug in u. But then you have to take the derivative of u. In other words, for example, the derivative of e to the x is e to the x. If I replace x with something more complicated, like x squared plus 2x plus 1, you're gonna get back the same answer. That is, you get back e to the power. And our power is this. But then you multiply by the derivative of, in this case, the power. X became more complicated. So you get the same answer, except, and wherever you see x, you put that more complicated stuff. But then you have to multiply by the derivative of it. We know that the derivative of x to the 7 is 7x to the 6. So I'm going to make x more complicated. I'm going to say x is 3x squared minus 9x plus 11 to the 7th. Well, we get back the same answer. But instead of x, we have this. So we get back 7 times what x is now to the 6th power times the derivative of this, which looks to me like 6x minus 9. If you know the derivative in terms of x, you get back the same type of answer, except instead of x in the answer, you put down the more complicated version of x. It's called the chain rule. The derivative of tangent of u is secant squared of u times the derivative of u. These you have to know. Can't play the game if you don't know the rules. There's nothing really to understand here. I mean, you can prove that the derivative of tangent of x is secant squared x. You don't just have to accept that. Our tangent x is sine x over cosine x. So I want the derivative of our quotient. The derivative of the top, the derivative of cosine x, or the derivative of sine x is cosine x times the bottom. Minus the top, sine x, times the derivative of the bottom. Well, the derivative of cosine x is negative sine x. So that negative is going to make this symbol a positive. It's going to make the negative a positive. And this all gets divided by the bottom squared. Now, what happened here? First, I write the derivative of the top, which is cosine x, times the bottom, which is cosine x, not cosine squared x. So, this times that, that's cosine squared x, plus this times that, that's sine squared x over cosine squared x. that numerator is 1. So you get 1 over cosine squared x. But cosine squared x in the denominator, I meant to say cosine x in the denominator is secant x in the numerator. But we have 2 factors of cosine squared x in the denominator. Ooh, look at this. We just showed that the derivative of tangent of x, which equals this, which equals this, which equals that, which equals that, which equals that. Secant squared x. You can prove the other ones using their definition of derivatives, but my advice would be to just know these cold. The derivative of cosecant x is negative cosecant x cotangent x. The derivative of secant x is equal to secant x tangent x. Nothing to understand here. Just accept them as definitions. The derivative of cotangent x, well, this is going to be negative cosecant squared x. Now, if I replace x's with u's, well, it's just Simon says. Replace all the x's with the variable u. And then, don't forget, take the derivative of u. Okay, these are the 6 derivatives that you have to know. It's not up for negotiation. You want to pass Calc 1, learn these 6 definitions. Be good if you can prove them, but I don't mind saying just know these as if they're definitions. So, what if you were asked to find their derivative of the sine of 3x squared plus 4x plus 5? The derivative of that. Well, recall that derivative of sine of u is cosine of u. The angles never change. Cosine of u times u prime. So we're going to get the cosine of u. That's u. We're going to get the cosine of u times u prime, which is 6x plus 4. And there is your answer. 6x plus 4 times the cosine of that angle. If you were given that y is equal to cotangent of 4x plus x squared sine x squared, and you're asked to find y prime, well, remember the derivative of cotan of any angle is negative the cosecant squared of the angle times the derivative of the angle. So y prime, the derivative, so it's negative the derivative of the angle times cosecant squared of the angle, which is notch 14. It's 4x. Plus the derivative of that. Well, that's a product. So you take the derivative of the first function, multiply it by the second function. Plus, you take the first function and you multiply it by the derivative of the second function. The derivative or sine of any angle is cosine of that angle times the derivative of the angle, which is 2x. So I would definitely clean this up. This is negative 4 cosecant squared of 4x to times, oops. So between here and here, they seem to have 2x in common. So we factor it out, and what isn't circled, namely the sine of x squared plus x squared cosine x squared, gets factored out. In fact, I didn't see that addition sign, so I was going to multiply 2x by 2x, but this answer right here is fine. In fact, the only thing that really is common and we should factor out is the negative 2. Can factor out a 2. I can factor out a 2 from there, a 2 from here, and a 2 from that term. So I get 2 times negative 2 cosecant squared of 4x plus x sine of x squared plus x squared times x, that's x cubed cosine of x squared. I factored out the 2. And I noted that x squared times x is x cubed. There's your answer. If these coefficients were the same, make believe that was an x for a moment. That's an x. So I have x times sine, nonsense what I was going to say. So even if that were an x, we don't have sine squared x plus cosine squared x. Okay, there is the answer. If somebody asks you this problem, you should be very thankful. If somebody said, calculate the derivative of sine squared x plus cosine squared x. Well, first you do your algebra or trig and you say, that's 1. This is 1. And the derivative of 1 is 0, and be on your way, and that's it. If you didn't know this, this is the price you have to pay. First, I would rewrite this as sine x squared plus cosine x all squared. And then we take the derivative. Take the derivative of this first and then add on the derivative of that. Well, this is some function to a power. The power is a real number. It's not a function of x. You bring down the power, you make the new power 1 less, then you take the derivative of sine x, which is cosine x, plus. You have cosine x to a power. Bring the power down, make the new power 1 less, multiply by the derivative of cosine x, which is negative sine x. So, we have 2 sine x, cosine x. This minus makes that minus, and then we have 2 sine x, cosine x. Oh, these are exactly the same, and with subtracting them, I know that answer. It is 0. Okay. Now, this is a pretty classic problem. I like this one. If you have this, you have 2 ways to go. One is to use the product rule. Let us just factor out the 2. So the derivative of y will be the derivative of this times 2. So there's my 2. And in there, I have a product. Sine x times cosine x. So it's the derivative of the first times the second, plus the first, which is sine x, times the derivative of the second, which is negative sine x. So we have 2 times cosine x times cosine x is cosine squared x. This makes their sign subtraction, or the operation subtraction. sine x times sine x is sine squared x, and you're like, well, that wasn't that bad. Another way to have done this problem is to realize that I didn't copy it down right. Realize that 2 sine x cosine x is sine of 2x. Sine of 2x. So y prime is, well, the sine of any angle is the cosine of the same angle times the derivative of the angle. Now you may say, wait a minute, we didn't get the same answer. And I would just ask why you say that. Those are the same answers. So what we discovered, we took the derivative correctly 2 different times, and the answer is 2 times this and 2 times that. Well, it must be so that cosine squared x minus sine squared x is equal to cosine of 2x. Okay, we just proved that. Like magic, it came out for free. We weren't even looking for it. I doubt any textbook out there shows the proof this way. And the main reason is that this here is a trigonometric identity. That is, you need it in trigonometry. But we got this proof from using calculus. And most trig students didn't take calculus. So that is why you'll never see this proof in a book. Alright, let us try some more. So, if somebody asks you to find the derivative with respect to x of sine x over cosine x, well, this is the derivative of tangent x. And we remembered that one. The derivative of tangent x is secant squared x. What if you were told that y is equal to the sine to the 4th power of 3x squared plus 9x? Now, whether you rewrite this or not, you have to think that it's like the way I'm about to write it. It's the sine of that angle to the 4th power. The derivatives, well, if you have a function to the 4th power, first you just play games with the power. You bring the power down, you make the new power 1 less. And then you go, okay, then I'm going to take the derivative of this. I'm not going to take into account anything I've done prior to this. I am going to take the derivative of this. Well, the derivative or sine of any angle is the cosine of that angle times the derivative of the angle, which is 6x plus 9. Okay, you can factor out a 3 from here, multiply it by the 4 in the front and get 12. And I'll say this first, but remember, I factored out as 3. Then I'll write this next. The cosine of 3x squared plus 9. Then I'll write the term being raised to the power last. The sine of 3x squared plus 9x, all cubed, so it's customary to put the cube there. And there is the derivative of this function right there. Suppose you were asked to find, dy dx at, let's see, at say pi over 2 comma 0 for the function sine x, or the equation sine x plus cosine of 2y is equal to 2. Well, before you can find the derivative at a point, you find the derivative and then you plug in the point. So let us find the derivative of this. With respect to x, the derivative of cos of sine of any angle is the cosine of the angle times the derivative of the angle with respect to x. Well, the derivative of x with respect to x is just 1. So I won't bother writing that. The derivative of cosine of any angle is negative the sine of that angle times the derivative of the angle with respect to x. The derivative of 2y is 2y prime. And the derivative of 2 is 0. So if you subtract two things and you get equal, immediately say those two things must be equal to one another. And I'll divide both sides by 2 times sine of 2y. Because then I just get y prime equals. Divide the other side by 2 sine of 2y. So now I have the y prime. It's in terms of x and y. It has x's and y's. But they want me to evaluate it when x is pi and y is 0. Okay, I can do that. Y prime at x is pi, y is 0. This is cosine of x, but x is pi, divided by 2 times the sine of 2 times 0. Okay, so this is the cosine of pi divided by 2 times the sine of 0. Well, the cosine of pi, well, it starts when x is 0 and it finishes one cycle at 2 pi. Well, smack in the middle is going to be pi. And the cosine of pi is at its lowest point. It's -1 divided by 2 times the sine of 0 is 0. So you get, it does not exist. That means you have a vertical asymptote at pi 0. Okay, here's pi 0 right here. You're gonna have a vertical asymptote. Maybe, I mean, I have no idea what it looks like. But when it gets to pi, it's going to be getting close to the y-axis. Either when y is really positive, or possibly when when y was real negative. I don't know. I don't care. When I'm above pi, I have no idea what it looks like. But I know that either it's going to get closer here, or it's going to get closer here. That means that the function is not even defined at pi 0. Let us see if that is correct. The function was the sine of x plus cosine of twice y should equal 2. Well, the sine of 0, actually the sine of pi, plus the cosine of 2 times 0. Now, I want to see something, please. Very interesting. Now, something's very much bothering me. So, the graph goes like this. It starts at 0, it finishes at 2 pi. So at the beginning, in the middle should be pi. the sine of pi is 0. Plus 2 times 0 is 0, so you have the cosine of 0 equals 2. Well, cosine of 0 is 1, and 1 equals 2. Well, that's not true. So, the real problem we have here is that I've been plugging in pi when they clearly told me to plug in pi over 2. Okay, so this is pi over 2. And what is the cosine of pi over 2? Pi over 2 is in the middle of 0 and pi. So cosine of pi over 2 is 0. So we have 0 over 2 times 0, which is 0 over 0. Wow. What does that tell us? Well, again, I'm concerned about, oops, just clean this up, pi over 2. I'm concerned that it's even defined here. Sine x plus cosine of 2y. Well, x is pi over 2 plus cosine of 2y. Well, the sine of pi over 2, well, that's pi. So from 0 to pi, pi over 2 will be right in the middle. It's 1. So we have 1 plus 2 times 0 is 0, because y is 0, and cosine of 0 is 1. So yeah, we are getting 2. So this point is on the original function. So what is going on with the derivative? Did we make a mistake calculating the derivative maybe? And that is what I'm checking right now. Okay, it looks to me like this is okay. Now I have a feeling I just blew the comment I made at the bottom. Cosine of pi over 2 is 0. Well, what's going to happen, say, as x approaches pi over 2? What is the limit as x approaches pi over 2 of the cosine of x over 2 times sine of 2y? But we're going to let y be 0. Okay? And the sine of 0 is 0. So that's interesting. How about we try it the other way? Suppose we let y approach 0. Let y approach 0 and let x be let x be pi over 2. So you get 2 times the sine of 2 times y. Well, the numerator is 0, and yeah, the bottom is going to be 0. Well, the bottom line is the problem asks for dy dx at that point. It's undefined. again, let us hold one of these. The limit of cosine x over 2 sine 2y. Let y approach 0 and let x equal pi over 2. So this becomes the limit as y approaches 0 of the cosine of pi over 2 over 2 sine of 2y. That numerator is exactly 0. It is exactly 0. Cosine of pi over 2 is a true 0 over 2 times the sine of twice 0. Well, if y is anywhere near 0, 2y will be near 0, but never 0. So the top is always 0, and the bottom will not be 0. Why? Because 2 is not 0, and anywhere near 0, anywhere near 0, not including 0 itself, that function is not 0. So the limit is 0. You actually have a horizontal tangent line there. Okay. Let us do one more problem. Suppose y is equal to sine x plus the sine of 2x. The sine of 2x, and say I tell you that y is defined only on 0 to pi. And we want to find dy dx. Dy dx is equal to the derivative of sine x is cosine x plus the derivative of sine of any angle is cosine of that same angle times the derivative of the angle, which is 2. For the record, I could have said that here. The derivative of sine of any angle is the cosine of the angle times the derivative of the angle, which is 1. So either way, I get cosine x plus 2 cosine twice x. And there is your dy dx. And this finishes this video entitled Derivative of Trigonometric Functions.